Welcome back, everybody. Today we're going to be doing part 3 of the Physics 1 series, and today we're going to be talking about the kinematics equations and finally getting into the formulas. And at the end we'll go over 2 examples, and hopefully I'll walk you through them. Hopefully I'll explain the best I possibly can, and I hope you're excited, and let's get to it. Alright, so let's first review what we kind of did the last episode or last series or last part of the series. And if you haven't watched that, make sure to watch that if you aren't clear of some of the concepts. I basically went over basic definition of some physical quantities, and such as displacement and distance, which will be definitely used today. So if you have any confusions, go check that video out. But anyways, so last time we talked about vectors and scalars, and we know velocity right here is a vector, and we know acceleration right here is a vector. We didn't talk about how to calculate them, but I did tell you guys that velocity was the rate in change of distance. So it was the rate in change of this distance, which was, or displacement, which was basically a vector, right? So from that, when I'm talking about rate, you can automatically think of it has something to do with something over time, because you want to rate is usually something like when we say that he's running at a rate of 5 meters per second or something, we're saying that he's running 5 meters every second. So given that definition of velocity, that means we can sort of infer that velocity must be the change in the displacement, or I'm going to say delta t here, over the change in time. So what this means is, what delta means is the final, so the final displacement divided by the initial, and that's essentially what I'm saying by delta. But usually in many cases for t, usually start at t is 0, so we can just essentially say it's just t. So what this is giving us is saying that the velocity is the rate in change of time. However, this formula right here actually is the average velocity. So I'm just going to write that here. Actually, I won't abbreviate it. So this is the average velocity. So that means that this is an average over this certain time period. So it's not the exact velocity at this time or in this time period, but it's the average velocity over this time period right here. So that means that whenever we use this formula, let's say, like I said, for example, let me erase some of this stuff. So let me actually put this equation or this formula to the right here. So again, V is delta t or delta x, also it's also used there, over delta t. So let's say, for example, I said that I walked my displacement was 20 meters to the right. So I'm going to assume that for me, let's say this was a number line. I think number line would be easier to explain. So let's say I was here like after 5 seconds, and this was 20 meters, correct? So if I said what was my average velocity, what I would do is I would use, since my displacement is 20, so I know my delta V, and I'll even write it out. So V would be, so since we know delta, or the delta of displacement or change in displacement, so it's be final displacement minus initial displacement. So my final was 20. My initial was 0 because that's where I started, right? So it would be 20 minus 0 over change in time. And it took me 5 seconds. Started was 0 seconds, right? So let me write that here, just 5 seconds, right? So, oops, okay, so then this would be 5 minus 0, which would give me 4. Now, if you recall, since this is velocity, right? Well, first of all, we need the units, right? So it is 4 meters per second. Now remember, that's the standard units. Now, since this is velocity, I need a direction. Now, obviously, I went to the right? So this is my positive direction, my negative direction. So I went to the right, so I'm just going to say 4 meters per second to the right. And that's essentially how you would calculate the average velocity. Now remember, this is not the instantaneous velocity. What that means, it's not the exact velocity that I was going at. So that means in between, at this moment I could have been at 10 meters per second. At that moment I could have slowed down to like 2 meters per second. That could have happened, but we're not taking that into the account. We're just paying attention to the total, so the average velocity. And I'll keep that there for now. So we might have to erase it for the equations on the right side, but I'll keep that for now. Now here comes acceleration. Now, if you recall the definition of acceleration, we said it was the rate in change of velocity. So how velocity was the rate of change of the displacement, this is the rate of change of velocity. So that being said, that means this must be acceleration is the delta of velocity over the delta of time. Again, this means that this is velocity of the final position. Let me write that a bit better. So velocity in the final position minus velocity in the initial position over the times at those positions, right? And again, sometimes this one isn't needed because usually t initial is 0. So that just essentially means that this point will be just t. So that's how you find acceleration. Now, just like velocity, this is also the average acceleration. So I'll give the exact same example here actually. So again, with this number line. So again, with this, and I'm at 0, that's my starting point, and I come to 20 meters, and I know my, so I'll do this. So it's 20 meters, and again 5 seconds, right? But at the start, even though I was at 0, my speed was 0 meters per second, right? Because I was at rest and I didn't do anything, so I wasn't doing anything. But at the end, I will say that, well, we got our we got it from the top, so we got 4 meters per second, right? That was my average velocity. But I'll say at the end, my average velocity was, I'll just say like 20 meters per second or something like that, right? So what this would mean is that if I wanted to find the average acceleration, right, what I would do here, again, I would do the same thing I did for velocity here. Instead, I would do for acceleration, so that would be final velocity, which is 20, minus the initial, which is 0, divided by the time, which is 5 seconds, so 5 minus 0 here, and that would give me 4. Now, since this is acceleration, we know it's a vector and its units are meters per second. And again, I was moving to the right, so this would be 4 meters per second squared to the right. So that's how you'd find the average acceleration. So again, just like average velocity doesn't mean that the entire time I was going at 4 meters per second. I could have been like here at 10 meters per second squared. I keep saying meters per second, I mean meters per second squared. So I could have been like here at meters per second squared. I could have been like negative meters per second squared, meaning like slowing down at some point. So it doesn't matter. Average velocity just looks at the starting point and the end point, and we don't care about the stuff in the middle. Okay? So I'm going to erase this stuff so we can actually talk about the kinematics equations. So I'm just going to leave this up here. So, oops, wrong thing there. So we got that part. So we got average, how to find average velocity and average acceleration. And we know that it's the rate in change. For velocity is the rate of change of time. And in fact, let me write that down because it's actually pretty important. So rate in change of displacement or distance here. So, well, it's rate in change of displacement, right? And different color, and I'll say acceleration is the rate in change of velocity. So again, so that's just a recap there, and those are the definitions that we have. Now here come the kinematics equations. So I think I'll just write them down here, and I won't. I know I'll go over something at the end. It's not too important, but let's just see. So I'll just write them down. So the first equation that we have is V final is equal to V initial plus acceleration times time. And let me just write all three of them down. We can actually no. I'll go step by step. So this formula right here. What it's saying is that basically here, this can actually be derived from this equation or this average velocity that we found right here, average velocity equation, so or formula. But basically, since we know acceleration, we said that it was V final minus V initial over time, right? Or since we said time initial was just 0, it's just time. If you were to actually multiply t over here, we'd actually get this. So we'd get AT is equal to V final minus V initial. And that would just give us V final equal to V initial plus AT. Exactly the same thing that's right here. Exact same thing. So this one actually can be derived from the average velocity equation, or average acceleration formula. Now, coming back here, so essentially that's all that states, so we can just derive that, and it will give us velocities, and if we are given like 2 of the velocities of time, we can find the acceleration. If we are given this velocity and the acceleration and time, then we can find the final velocity just like that. So next, this is a formula for displacement, and this is delta x is equal to v initial times time plus 1/2 at squared. Now, this one, what this is essentially saying is, if you think about it, it takes into account for the velocity at the initial point and the time, the time duration of the travel, and then it takes account of the acceleration. And this at squared will make more sense in the next video when we talk about the graphs. But essentially, this is how you find displacement of an object in 1D kinematics, essentially. Then lastly, we have one more, and this one is actually actually pretty useful in many cases. So it's v final squared. Let me write that squared a bit better. So v final squared equal to v initial squared plus 2 times acceleration times the displacement of x. So oops, I think I ran out of space there. Let me make that a bit smaller. So displacement of x. That's an x, okay. So basically this formula essentially just helps us get final velocity or initial velocity if we aren't given time. So if we're not given time, we definitely want to use this, and that's actually very common in some of these problems where you're not given time. So as you can see, all these three equations right here, right? They all have something missing, and you have to figure that out when you look at a problem. You gotta realize what you have. So in kinematics, it's usually a good idea to list out what you have. So I'll show you in cases where I'll just list out, okay, I have v initial, I have t, I have a, oh, okay, I need to find v final. I could use, for example, this formula. So that's essentially a really good idea, to list out what you actually have and what the question wants you to answer. Now there's a thing to these three equations. So what these three equations rely on is that in these cases, and it won't matter too much in physics 1, but in other higher level physics it might matter. For these equations to work, your acceleration must be constant. So what that means is you must be uniform acceleration. So your acceleration can't be changing. So you can't be at 2 meters per second second squared and then be at 5 meters per second squared. In that case, these equations will not work all the time. And there's actually another kinematics formula which is sort of useful, but it's not too necessary, which is related to displacement. So if you want to find the final distance or the final position, you can do x final. Just let me write that better. X final is equal to x initial, so the starting point plus your velocity times the time it takes you to reach this final position. So why this formula is also kind of weird is because this formula is dependent on your velocity being constant. So your velocity must be constant in this kinematics equation for this to even work. So these are really the three main equations or formulas that you need to know. The rest are also important, but these are just the main ones, and this is just a brief overview, and you're going to have a lot of practice with these, so it'll make a lot more sense. I'll be going over a lot of practice actually on this, so let's get to the actual practice problems now. Alright, so let's get into this problem. So what this problem, you can take, if you want to take time to read it, you can, but what essentially I'll basically summarize it is saying is there's a race car, right, that accelerates uniformly, so that means that the acceleration is constant. So that just means that we can use our kinematics equations here. So what it's saying is it accelerates from 18 meters per second, so this is our initial velocity, and to 46.1 meters per second, and that's our final velocity, and 2.47 seconds, so that's our time. So like I said, you want to list out what you have. So I'll just list these out. So we have v initial, or velocity initial, which is 18.5 meters per second. We have velocity final velocity, which is 46.1 meters per second. And then we have time, or t here, which is 2.47 seconds. So given that, first we want to find the acceleration right here. Let me do a better color. That's not too obvious. So we want to find acceleration. Okay, that wasn't a better color, but anyways, we want to find the acceleration. Now, in this problem, it might make sense So what we'll do is we'll use the first kinematics formula. So what that means is we're going to use this formula because we're not given acceleration. We are given v final. So this is the formula. Let me write that out. So which is v, or v final, is equal to v initial plus at, right? So that this formula, since we're given this information, time, we can just find acceleration. So acceleration is just going to be our v final minus v initial over t. And I just essentially basically just subtracted, so I get v initial is equal to at, and then t is equal to v minus v initial over or sorry, not a is equal to v minus v initial over t, right? So that is what we need. So if we were to do that, so that would be 46.1 minus 18.5 divided by 2.47. This would give us around 11.2 meters per second. I just rounded up, but meters per second squared. So that would give us 11.2 meters per second squared. And we're not really given a direction here, so I'm just going to say to the right. I'm going to assume my positive direction. If this were the track that the car were on, I'm going to assume that it went this direction. It went to the right. So that is our acceleration. Now I'm going to erase some stuff, but let me just write our answer for acceleration here. So I'll just write all our answers here. So our acceleration, we got 11.2 meters per second squared to the right. Right. So that's our answer for the first part of the question. Now for the second part, it wants us to find the displacement or the distance traveled, right? So now we know acceleration, and now we need to basically just find displacement. So I'm going to use the second formula, which is delta x is v initial times t plus 1/2 at squared. In fact, we could have also used the third one. Actually, let's use the third one. I want to use the third one because it's also sort of cleaner in some cases. So third one, which was v final squared, is equal to v initial squared plus 2 times acceleration times displacement. So now we just want to find displacement x. So I'm going to solve for that. So what we're going to get is, if I just bring all the velocities to one side, we're going to get, we just need to do a simple math here, just bring not like terms together, but just substitute or solve for delta x. So we're going to get delta x here is equal to v final squared minus v initial squared over 2 times acceleration, and plugging all these values in. So be 46 to be 46.1 squared minus 18.5 squared divide by 2 times the acceleration that we found, which is 11.2, and that would approximately give us around 79.6 meters, and that is what we got. And again, since this it just wants distance, it doesn't want displacement, so this is just going to have no direction, because since displacement or distance is a scalar. So this is our second answer. So that's essentially how you solve a simple kinematics equation. So just to review, or problem. So just to review, you basically list out what you're given, and then you want to see what the question is asking. It's the first part asks acceleration, then it asks for distance. And you can basically, since all the kinematics equations have one thing missing, if that one thing missing is what you're looking for, and you have the other parts of the equation or the formula, then you can just use that formula, just like we did for acceleration, and here we did for displacement. Now on to question 2. Alright, so question 2. So this question is actually a bit more interesting, and we'll see that. So here we see a feather is dropped on the moon. Okay, so the height 1 point. So this one, so last question we had our question on the x-axis, right, or the horizontal axis. However, this question is on a vertical axis, and since it's on our vertical axis, you might think that, oh, maybe your equations change, but no, they do not change. These kinematics equations work for any kind of kinematics problem in one dimension. Now, when you get in 2 dimensions, you're going to have to split into components, but you don't have to worry about that right now. So right now we see that, okay, it's just up and down. So what that means is every time or everywhere in our formulas where we had y or x, we're going to switch that to y. So our delta x, or what we had that would be delta y now, because everything's in the y direction. Now We haven't talked about gravity on Earth and what the value is, but that doesn't matter because this question's not on Earth. So that was not a pun, by the way. But anyways, so this question's not on Earth essentially, right? So basically, let's just look at what we got. So we got our displacement, or our height, which is 1.40 meters, and then acceleration of gravity on the moon. So this is going to be gravity, which is essentially, again, just another way of saying the acceleration of the object is just going to be this 1.67 meters per second. And we want to determine the time that it takes for the feather to fall on the surface. So let's think about this. Let's actually draw this out. So let's say, okay, I'll just draw out the moon. So let's say this is the surface of the moon, and this is my feather. I'm just gonna like make a box, right? So this is the moon, or this is the surface. Like this is the feather, not the surface. Okay, so this is the feather, and what we're gonna do is, so we're given that the height is 1.4 meters. And so that just means that this block or this feather is going to fall all the way down to the surface, right? So what this means is, if you think about it linearly, or what it basically means is that since our delta or displacement in the y direction is actually a negative number, right? Because we had so we have to think about directions, right? Because our displacement is a vector. Now what that also, so basically since we dropped down 1.4 meters, that means it's going to be 1.4 meters down, or in the down, right? So the down direction. Or I'm going to just simplify it and assume that my upward is positive and my downward is negative, right? So that just means my displacement in y is just a negative number. So if I were to write that, so that my displacement y is just a negative 1.4 meters. Now, here we have our acceleration. It's given to us as the magnitude of 1.67 meters per second squared. Now, think about gravities, it's always acting down. It's always pulling, or it's always acting down. So let's say, for example, when you jump, you know you're always going to come down because the gravity is pulling you down. So that means this is also in the downward direction because acceleration is a vector. So now you might have a question. So since we got our acceleration, and that's according to my system is negative 1.67 meters per second squared, you might have a question. What if I say my top is negative, for example? So I'll say everything going up is negative and going down is positive, and you set it up that way and you got your values, like, so then in that case it would be, everything would be positive, you're still going to get the same answer. And that's just the beauty of kinematics. So well, no matter what your reference frame is, and this is called a reference frame, so it's like your frame of reference, or what you think should be the directions of the signs and that kind of stuff, no matter what your reference frame is, you're always going to get the same answer. So you don't even have to do this. You can make your top being negative and the bottom is positive. It's up to you. So getting back to the problem, we see that it's going to fall down. We want to figure out the time. So since it's dropped, and we're not given anything but the initials right here, and usually when you're dropping something, right, it's initial, at 0 meters per second, right? It's not moving, you're just dropping it. So we can actually assume here, and many of these problems like this, you can actually assume that your initial velocity is 0. So now we're given change in the y direction, and we're given acceleration, we're given velocity. Now we just need to figure out time. And how we do this is we'll use our equation, which was for delta x. Here it's just delta y. So we'll use v initial t plus 1/2 at squared. Now since our v initial is 0, this makes this entire term 0. So that means I can just cross it out, and I'm going to get delta y is equal to 1/2 at squared. Now for time, I'm just gonna isolate for time. So I'm going to get t squared is 2 times delta y over a. So our t is essentially square root of 2 times delta y over a. Now I'm going to just bring an arrow here. So if we plug everything in, these values that we have here, if we plug them in, we're going to get around 1.29 seconds, and that's the answer. So I hope you enjoyed this video. I hope these practice examples helped. We're also going to have more practice examples next video, but I hope you liked this video. Please like the video if you liked it. Subscribe to the channel if you already haven't, and I hope to see you soon.